So maybe some of you have different values, have learned different numbers. 99.73 is how many are within 3 standard deviations. Okay, so you need to remember that. Okay? And we're going to use this. So let's go back for a moment because that's the last page. Let me go back and see. Tell me, were these distributions that we looked at? So here's the example that we did with the spending money, right? The spending money. Was this a normal distribution? We calculate a mean, a standard deviation. It's a small data set, but if we tried to say, oh, it's approximately normal, would you say it's a normal distribution? 99.7 is pretty standard in statistics that I've taught. 98. I don't know how you get 98, Ariana. It's not 98. It's 99.7. I'm not sure where you got that. Check your textbook. You remembered it wrong. You have some different numbers, 68.5, 95, 98. They're not precise. It's 98, 95, and 99.7. Check your textbook, Ariana. Okay, so I was asking, yes, so this is not, remember the spending money, this is not normal. There are no outliers in the data set. And within 2 standard deviation, we see all the data. That's not normal. Okay? Even though it's symmetric, we assume symmetry, it's not normally distributed. Okay, yeah, it looks like you guys are absorbing this, which is good. You're digesting it. Let's say that. I don't know if you're absorbed yet, but all right. So we're going to see an example of this. I'm going to show you how we use that. Don't lose those pages. Do you want any more clarification on this? Let's just do one where you guys can draw it. Let's say, for example, let's say it was the height that we care about. We write x is normal with a mean of 64 and a standard deviation of 2. So this represents the mean, and this represents the standard deviation. And the way I've written it, these are the parameters of the population of heights. So how would you draw the normal distribution for that? Why don't you sketch that for yourself? Debuja. So this means distributed, normal, mean, standard deviation. You know what I'm going to do is I'm going to cheat and just put them under here, because I don't want to make a mess. Let's see if I just move this away, and I'll put the numbers underneath. So what you have to do is say it's 64 in the middle. Then you're going to move over to 62, 60, what am I doing? 60, move over to it's 66, 68, and 70, and then backwards it would be 62, 60, and 58. That's how you would draw that. Same shape with 99.7% in between. Okay. All right, let's move to the second document. 5.2 has the solutions to this one. Am I going too fast? Tell me. We're going to apply this so you'll see the relevance of what I'm doing. So this one just has the solutions written out in a neat way so you can verify what I did in the video. So it's not as important to do the calculation as to understand what I'm doing here. And this is for the other one. Okay, so you have those solutions. And you need to know the difference between ex ante and ex post. And now we're moving to correlation. So everything I've talked about so far is one variable statistics. Okay, we talk about one variable and characterizing it, deriving its distribution, and then using the distribution to make predictions. What if you have two variables? What do we do about two variables and trying to understand the relationship between two variables? And you can do the same sort of thing. You can analyze them separately, but then when you put them together, you want to talk about how do they correlate? How do they relate? What is the relationship between them? So that, like any other data set, you begin with a drawing, a sketch, a visualization of the data. You look at scatter plots, for instance. You create two dimensions, the two variables, you create a two-dimensional graph of the data. So you have pairs of data, and you look for the regular pattern in the data, and you look for curious things about the data, or surprises, or unanticipated values, or points in the scatter plot. So this drawing is called a scatter plot. You should be able to describe the overall pattern in its form, if it's linear or nonlinear, and then comment on the strength of that relationship and the direction of that relationship. And in particular, we care about linear relationships. So you should have your calculator with you. We're going to work with your calculator in a moment. So if it appears reasonably linear, then we can use statistics tools to help calculate that line relationship, and use that line to make predictions. So we're going to say, if X is something, what can we expect from Y? That's what we're going to do. And we're going to pick X and Y in a way so that the one that's on the X is the explaining variable. It explains the other one. The other one is the one we're trying to predict. Okay, so we call X, the one that goes on the X, usually the explanatory variable. The Y we call the response variable. There's some other terminology for these variables that you probably have seen. This is called also the dependent variable, because it depends. So Y is the dependent variable that depends on X, or the explaining variable. So in that sense, using the word dependent, then X is independent. Okay, let's see. So you would look at the relationship. If it's not linear, maybe you have a curve type relationship, or maybe you have clusters, okay? It's important that you note what you found descriptively, and if you have higher level statistics course training, or you're capable of reading statistics manual, or well, even if in economics, you can learn how to transform this variable so that you can make it a predictive relationship. But the things we learn about linear relationships don't apply to curved ones unless you transform them into a line, and you can do that with anyway, I'm not going to get into the transformations, but you can do that if you learn how to do that. You can also have clustered relationships like this, and often you will only know that there's clusters if you draw them and you look at them and you observe that some of the data is set apart from the rest of the data, and if we separate the data, we have a different interpretation. For instance, if I look at all of the data and I say, is there a line over all of the data? Well, maybe I would come up with that sort of a line there. Now, what's wrong with that is, well, clearly the observations are grouping together in clusters. We call those clusters. And those clusters are not positively related. Like as x goes up, y goes up. That's what the green line seems to predict. But that's not what's happening in the clusters. The clusters, as x goes up, y goes down. So which one is correct? Which one should we, you guys tell me. Line 1 or line 2 and line 2. I'll call them 2 star and double star. Which better explains the relationship among those observations? Line 1 or the others? Okay, good. So we have our students that are taking a chance. Lines 2, correct. Right. So why did you pick those ones? Why not line 1? What was your justification? When we talk about correlation, we need to talk about form, strength, and direction. Okay, so in terms of form, strength, and direction, it's very important, it's critical which one you pick. So you guys picked this, and it's clear that these lines capture and explain the points better than that single line that goes through where they were all scattered around. So this is a good replacement or a prediction line for those, and this is a good prediction line for those. What we would have to do after we see the clusters is find out, identify, what divides the values, is there a third variable, another variable that divides the values, observations? In this case, the story I tell is it turns out that this group of individuals is distinct from this group in the number of hours they watch soap operas. Okay, so these are novelas on television, and this group watches much more than this group. But in terms of the other variable, they have about the same level of well-being. Maybe I can put a few more dots there. So it looks like, first of all, let's talk about what's happening. The relationship between watching soap operas and well-being is a negative relationship. So first of all, we see the line, and that's the form. We see a negative relationship. That's the strength. That's not the strength. Oops, that's the direction. That's the direction. And we see strong relationship. Now the negative means the more hours an individual watches telenovelas, the lower their reported well-being. So as this one goes up, this one goes down, right? So as we're moving up, it's going down rather than going up. And I'll talk more about that shape or that direction in a moment. Right, the point should be close to the line. If we did line 1, we could make the line, but it wouldn't be very good, and it doesn't hit many of the points. And anyway, it's not very representative, and it won't be good for prediction. So we go for line 2, the line 2s. So what is it saying? It's saying the more hours of soap operas are watched, it happens that the individuals are less happy, less content, a lower rating of well-being. So does that mean watching soap operas makes someone unhappy? Could, but not necessarily, right? There's no proof of that. I'd have to do an experiment to prove that causal relationship. But what I see is an association that people that watch a lot of soap operas are less happy. So people that watch more soap operas, they could be people that are, the people that watch more in their group could be people that are unemployed. That could be why they're unhappy. They could be people who are disabled or they were injured and they're recovering from an injury. They could be unhappy. So there could be different reasons that have nothing to do with the soap operas themselves. Although soap operas can make you depressed if you watch them too much, I'm convinced. I'm not saying that here. Because you watch them and you see their house and you see their clothes and you see their wealth and you think, oh, look at me. I want that. And that's not good for anybody. So, but I'm not saying that here. I'm saying that, and I made up these numbers. This is not real data. Just showing that there could be an association where the group could be defined by gender. This could be men, and maybe women tend to watch more soap operas. So that could be divided by gender, but then the relationship is the same. That the more hours of novellas you watch, that seems to be associated with being less happy. Okay, so that, like I said, it could be people who are unemployed. They have nothing to do. They're alone. They're isolated. They're sick, and that's why really they're sick. So the hours of novellas acts like a proxy for picking up general sense of well-being in this case, without having information on anything else. Okay, so hopefully you followed that. If not, watch the video again. All right, so let's talk about lines then. Ignore this. I don't have an example 2. I should probably edit that. This is just from other notes because I cut cut this from some other notes that I had. And I brought it down to just a few pages. So can we predict the height of children if we know how much milk they drink? Let's say we had data on that. Now there's many reasons why a child, there's many things that affect the child's height. And milk nutrition might be one of them, okay? So can we make predictions? Can we predict, general well-being from hours of novellas? In this case, it looks like we probably could. Such a tight relationship. So it depends on how good that fit is to the line. And then we want to talk about actually calculating the line. We begin with a statistic. So far you've learned about means and standard deviation. We talked something about percentiles and medians. Another statistic, and this is a critical one for this finance class, is the correlation coefficient, R. R captures the direction and strength of a linear relationship between two quantitative variables. So your variables have to be quantitative. So for example, can't be categorical data like gender or categorical. I'm trying to think in terms of finance. I'll just leave it like that. That's my best example. So to calculate a correlation coefficient, the variables that you're using have to be quantitative. In finance, that's easy. Lots of quantitative variables. And it'll tell you the direction of the relationship, the strength of the relationship, as long as it's linear. Okay, if it's not a linear relationship, you can't use R. You got to use something else, or you have to transform the data in order to calculate R. So I've drawn some examples here of what R means. So data like this, or what R is. So R is a number between -1 and 1. And it tells you, again, the direction and strength of a linear relationship between two quantitative variables. If R is the highest, the positive one, the data looks like this. Fits perfectly on a line, and it's a positive sloped line. Here, the data is more scattered, but still it's positively sloped, and they're not so scattered. It's pretty clear the data is going up, and this would be something like an R of 0.8. Here's an example of the other extreme, R of -1, perfectly negative on this line that's down sloping. And this is an example of more scatter than the one above, but it's kind of going down. So there's still a negative, but I'm going to say -0.5. Okay, so R is always less than 1. And these are the best you can do in either direction. Now there's these two other possibilities. This is an example of R equals 0, where there's no relationship. And here's an example of a non-linear relationship. It means there's a relationship, but it's not linear. And it can still be used to make predictions. As long as you find out this parabola, the function, you can make predictions of what will y be when x is a certain value. So you can use x to explain y all the way up the curve. If you were to calculate R in this case, does anybody know what you would get? You shouldn't interpret it, but what would R be here? So I'm going to get back to that question in a second. I want to show you what R does, and then we're going to talk about the formula for R, which you need to know. That's not good. Let me do that again. Okay, what I'm going to do is I'm going to show you how to interpret R by taking just this one here. What we're going to do is we're going to divide the data over its range. So the range of X is between here and here. So the mean is somewhere like about here. So I'm going to make a line through the data. Okay, so that's like the mean of the X's. And then looking in this direction, one is asking me a question, maybe not a prediction, rather an observation. Well, we're predicting. We're predicting from the observations. Okay, so in this direction, the values, oh, construction is starting. Oh, well, hopefully you don't hear that. And in this direction, I'm going to divide it in half. So where statistics is about means and relative measures, what I'm going to do is consider the data in relation to its mean. I'm going to look at this variable first, X, and I'm going to call this any observations above the mean as high and below the mean as low. And similarly in this direction, I'm going to refer to the region above the mean of y bar as high and below the mean of y bar as low. And I'm going to ask you, when X is high, where is Y? Is Y high or low? Where does Y tend to be? So when X is high, where do you find the observations? Above or below Y bar? So when X is high, where are the observations of Y? Above or below Y bar? High or low? Where is this? Why do you say below? When X is high, where are the red dots? High or low? Diego, got it, above. So it's high. So when X is high, Y is high. You see, they reinforce each other. X is high, Y is high. What about when X is low? Where's Y mostly? When X is low, Y is where? Mostly. Well, there's two observations above Y bar, and there's all these ones below. Yeah, you guys wrote it wrong. But I'm pretty sure you knew what you were doing, but you just wrote it wrong. So when X is low, Y is? Low, very good. So when X is low, Y is low. When X is high, Y is high. When it's reinforced this way, this is known as a positive relationship. When the X and Y tend in the same direction, they behave similarly, okay? So this is known as a positive relationship because one reinforces the other. The strength of the relationship is reflected in how close we are to one. And in the graph, it's how how consistent that interpretation is. Let's try another one. Let's try this one down here. It's not as good, but let's try and divide the data in half. So I'm going to eyeball like here. And then y divided in half is like, oops. And what do you see here? It's not so great, right? It's all over the place. But we're going to say mostly. So when x is high, where is y? So when x is high, where are most of the values of y? Y is low. And when x is low, this is a little stronger, y is mostly up here, right? It's tending to be up here. So we're going to say y is high. Okay? So this opposite, these are opposing. In that sense, we see this is a negative relationship, and it turns out when you calculate R, you get this negative relationship. And so that brings us to this one. I'm back to the question. What would be the R here? Can you calculate that? You can do the same thing, divide the data in half. Even here, let's do it here first. So if I divided this in half and this in half, it's not so clear, is it? It's even less clear than what we saw before. So this, in this case, x is high and y is high, but it's like in both, isn't it? I actually think my bar needs to be higher. Hold on, let me go back. I'm gonna make my y bar a little higher. And it just goes right through. And you see I have about the same amount in each quadrant. So it's mixed. So we would say in this case, so the R we're going to talk about in a second how to calculate it, but I'm showing you what it's capturing, okay? So here, if x is high, above its mean, y is in both. And if x is low, y is in both, high and low. All right, there's 4 and 4. So that's what makes an R of 0. It's not a clear pattern. There's no relationship, no linear trend. So finally, let's do this one. If I divided this in half, I think it'd be like a little bit over here. And then through here would be like here. And do you see the same thing that I just saw above? So what would R be? So here, X is high. When X is above its mean, where's Y? It's in both. And here, when X is low, Y is mostly low. But this is enough to say that R is close to 0. Okay. So that will look like there's no relationship if you never made a graph and you just calculated R in the computer, because you can do that. You can even do that with your calculator. I'm going to teach you how to do that. But that doesn't mean there's no relationship. This is actually a relationship. You need to see the graph, and you need to rule out calculating R. You should not calculate or interpret R here. Okay. Oh, I wrote a big R. Make it a small one. Questions? But if you did, you'd get an R of 0, but that doesn't mean there's no relationship. There actually is a pattern. Okay, so what we're going to do next is calculate R. And we're going to do that with finance data, okay? I'm going to talk about the formula of R. And nobody's making any comments. You guys good? And we're going to jump into the finance stuff. So let's get 5.4. So maybe you read through this already, but it's really important to see where I'm going with this. So I put everything on one page. Maybe it's a scary page for some of you, but you'll appreciate it later because it's all on one page. So here we have financial data. You have information on Bell Canada Enterprise stock returns. Now don't get confused that I'm working with percentages and then we're going to talk about expectations in terms of probabilities or things like that. Remember, that's the units here, okay? So if I looked at women's heights, it would be inches. If I look at dollar sales, it would be dollar units. In this case, it's percentage are the units. So this is the return to a particular stock. And this is the return on the S&P 500. This is a market index. It tracks the top 500 companies and comes up with a value that it tracks over time. So it keeps tracking the 500 companies, comes up with a return. We're going to talk about how they calculate returns. Well, we're going to use basic approach, but you can get a simple version of what's being done to calculate returns. But okay, so this is a measure of return on the stock market. So somebody invested in a portfolio of stocks that represents the risky assets or stocks in the S&P 500, those companies, the top performing companies. If they have a 15% return in their investment, in their portfolio, or somebody can actually invest in an index that tracks the stock, right? So you can invest in an index and you can get the return of a managed portfolio without actually managing yourself. But there's fees and costs to doing that, and some people like to avoid that and manage their own portfolios, but most people don't. Most people just use a fund manager invest in index. So here is a 15% return. When there's a 15% return on investors in the stock market, represented by the S&P, the top selling companies, then BCE stock does give its investors 30% return. And we'll talk, like I said, about what return means soon. When the market return is 9%, BCE returns are 8%, and so on. Okay, so this is historical data, ex post data. This has happened in the past. These are the returns. I haven't told you what kind of measure that period interval is, but anyway, those are measures from the past. Now, looking at that, is there a relationship? What is the relationship between those variables? So when I say relationship, there are two variables there. And what should you do when you get data? First thing you should do is make a scatter plot. Why don't you make a scatter plot of that data? What do you see? How do you conclude? I want you to make a scatter plot and I want you to comment, is the relationship linear? I want you to comment on the strength and the direction. Okay, so Paula's saying y is double x, and they move together. Okay, so answer the questions, Paula. The linear, the strength, and the direction? Tell me. Is it linear? Okay, so someone said it's linear. Yes, it's positive. And what about the strength? Did you draw it yet? Strength. You could say strong or perfect. It's exactly double. So that's how you answer all those. The plot, I'm sorry, let me see. So how would we plot these? So you probably had to think, well, which one do I put X and Y? I actually told you which one to make X and Y. And it turns out always, 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 always in finance, at least in this class, market index is explanatory. We're going to use the market performance to predict stock return. So if you drew this, this is what you would see, because I know I can see you didn't draw it. Or the ones that are drawing are quiet, and the people who are responding are seeing that it's double. Now, how does the double figure into things? So if you plot this, you will see the dots go like 2, 3, 4, 5. That's how the dots go. Perfect line. R is 1 because it's a perfect line. It's positive, and we have a line. So what do we do about the 2? What is 2? What is the doubling? What does the doubling mean? What's the doubling? What is the doubling? Where does the doubling come into this? R is 1. It's positive. It's perfect because it fits perfect on a line. It's perfect, strong, positive relationship. But where does the 2 go? Okay, you guys don't know. Okay, so let's do this. Take out your calculators, and we're going to enter this in our calculator. And I hope you remember how to do this and you remember all the results, because I don't want you to lose sight of what's happening, okay? Because underneath everything are all these formula here. So we're going to get all of these from the calculator. So let's take out the calculator, and I'm going to use the data stat. So if you watch the video, you learned how to use your calculator for statistics, right? So I'm going to hit second data. There's something in there, so I need to erase it. So second clear work. So it's clear now. So I have to clear the worksheet for data. And I begin entering data. Oops, I didn't want to do that. I begin entering data. And the data are from X. The first observation is 15. I can enter it as 15 or 0.15. Let's enter it as 0.15. And you don't have to, but it's something I learned to do to avoid some confusion. Okay, don't worry about that. Just enter them as percentage decimals. Okay, so 0.3, enter. The second observation is 9, so 0.09, enter. And 0.18, enter. And for the third one, it's 0.1, enter. And the pair is with 20. So it's always double, right? And then 4 is 0.075, enter, and then 0.15, enter, right? Because it's double. And the fifth one is 0.08, enter, and 0.16, enter, enter. Everything is inside. Okay, so did you see that? I'll give you a moment to comment. And do that, make that calculation. Miguel's getting closer to the point. So I have all the data in there. I can see it. 0.15, 0.3, 0.09, 0.18, 0.1, 0.20, 0.075, and 0.15. And finally, 8 and 16. Then I ask for statistical results. Oh, you want me to repeat, Ariana? Okay, so let's clear second clear work. Oh, sorry, I got to go into second data, and I have to clear it while I'm inside. So second clear work. And I enter the values. 0.15, enter. 0.3, enter down. So using the arrows for the pair. So then 9 and 18, 0.9, enter down, 0.18, enter down. Now the next pair is 10 and 20, right? It's always double. Enter down, 0.2, enter down. And the fourth one is 0.075, 15, 0.075, enter down, 0.15, enter down. And finally 0.08, enter down, and 0.16, enter down. And that's it. Okay, I'll give you a minute. When you're ready, hit second stat, and then you can scroll through the results. You scroll through the results. So second stat, and it says lin. Lin for linear. Lin for linear. These are the linear results, as though you're Your calculator is assuming that's what you want. You want the linear relationship results. So you're going to scroll down and see there were 5 observations. Little n means the sample size. That's the mean of the x's. That's the standard deviation of the x's for the sample, thinking that it's a sample. And this is if you think it's a population, so we ignore that because we know it's just a sample of historical data. Then y bar is for the y's, that's the mean. And this is the standard deviation for the y's. And this is the population one, which we don't need. Finally, we get this number. A. Oh, what happened? What happened to my results? This is not right. These are different. This is some other data. Oh, what is happening? Did I enter something wrong? Let's go see. Second data, 0.15 and 0.3. Oh, that's why. 0.3. Yeah, that was weird. And then 0.09, 18, 0.10, 20, 0.075, 0.15. Okay, starting again. That was weird. Those numbers look familiar, but I messed up with the y. That's when I started seeing the problem. Okay, so second stat. One more time. Yes, that's right, Paula. I had a typo on my y's. All right, so then x's are all good. And then y, that's the mean, that's the standard deviation. And I'm going to explain why you need those. But all these results are here in your calculator. There's your standard deviation. Okay, so A is 0, B is 2, and R is 1. What do these mean? What's A and B? What are A and B? So you get all the center and spread, mean and standard deviation, and then you get A and B, and R is 1. So what does it mean? What you found is the line. You found the best fit line to the points. You found out that A is 0, B is 2, and R is positive 1. So what you found was A is the y-intercept, so it just goes through here, right? B is the slope, so the slope is 2. So this is the y-intercept. That's where it crosses here. And this is the slope. So you found it all. The slope is the sensitivity of BCE returns to market returns, or market behavior, market performance. How do we interpret the slope? And now we'll go back to what somebody said above. It was Miguel. Miguel made a point. So B is the slope. So you see everything here? So we know that it's linear. Just looking at the numbers, we didn't even have to draw any of this, but I wanted to make the point to you first that the relationship is perfect. Everything falls in a line. The line crosses through 0. And there's a slope. That's what this relationship is. So we interpret for a B. Let me maybe make this bigger. I'll put it here. B equals 2 means 2 over 1, right? So you interpret from here. So remembering the units, right? The units are percentage. So 1% change in x implies, or we'll say for each, we'll say for each. For each 1% change in x, y change by, okay, let's not use change because it could be positive or negative. So I could say, well, I'll say change. Y changes by 2%. So the interpretation for slopes is always to use the units and interpret from here and say for 1 unit change in x, y changes by that, because the slope is change in y over change in x, correct? So you could say an increase. So when the stock market goes up by 1 unit increase, then BCE returns go up by 2 units, or 2 percentage points. So that means it's sensitive. Why am I saying sensitive? Why am I using that terminology? Well, it's nice when things are going up, but what about when things are going down? If S&P 500 goes down 10%, what happens to BCE? So if S&P 500 goes down 10%, what happens to BCE? It goes down double. BCE will go down 20%. So that's the sensitivity thing. That's not great. It's great when the market is up, but when the market is down, it's sensitive and risky, right? It's a measure of risk. It is a measure of risk. Okay, so that's where we're headed with this. Let me talk about these formula, and then don't forget this. This is the big picture situation. This is what we're headed to do, but you need to know the formulas because I'm going to play with the formulas. And you need to know what they all mean. So, for historical data, so let me make some last points here. Well, I'll do it below. Okay. So for historical data, we compute a sample mean like this, right? Sum up all the numbers and divide by n. That's our measure of average. And the standard deviation of the x's is the square root of the variance. The variance is an average of the squared deviations from the mean, adjusting for the fact that it's a sample. So that's okay. You guys know how to do that. And then there's this term. What is this term? This term is a more general version of this. This is called the covariance. Covariance. Why? Let me expand this a bit here. What if I wrote what is that? Statistics is about averages and relative measures. All these averages. These are all just averages. And it's like an average and a relative measure mixed together. So what is that? Do you recognize what that is? No one? What if I wrote it like this? I'm waiting. Okay, variance, Tanya. So this is a variance, right? So this is like covariance of x with x is really the variance. So it's a more general measure of tendency. Here I'm seeing the relationship of x with itself, and it's capturing how spread out the data are, right, for the variance, and then I take the square root to get the standard deviation. But when I do covariance, I'm looking how the variables covary, how they correlate, but I'm doing it with their actual unit values. So this actually tells me the direction of the relationship or the trend. Between x and y. The problem with it, I mean, it's useful in getting us where we want to get. The reason, what we end up doing is converting this, because the values of the variable help us determine in relative terms, is that high or is that low? You know, is that very much above x, well, the expected value of x or x bar? Is that much below the value of y or the expected value of y? So to do that, we standardize this value to get R. So R is actually a standardized covariance. That's what R is. Now, I have here 3 formula, different ways you may have seen R in the past, but this is the one we're going to use mostly in this class. You need to remember the relationship between covariance and correlation, and not forget how to calculate covariance. It looks like a variance, but you're using x and y together, and then you standardize it, and by standardizing it, it reduces it to an index between -1 and 1. and then we can interpret it. Otherwise, for covariance, we'll get some number. We don't know what it means. All we would know is we look at the sign and we can say, well, that's a positive direction or a negative direction, positive relationship or a negative relationship, but we won't know how strong that relationship is because we don't know how close everything is together. And by standardizing it, we're able to scale it down to -1 to 1, and that helps us interpret. So it's pretty brilliant, actually. So that's the relationship between those two, and these are different ways to see it. Mathematically, you can see how this happens. I could just move this. This is just in front here, and I can just put the SX, XY, SY here. But if you look at it in this form, this is still R. In this form of R, you see what's really going on. And I like to instruct when I teach R, I teach using this, but I did it graphically with you earlier. What I was doing was showing you when X is high, what does Y do? Because look, this is picking up the signs. So for instance, let's say we have the relationship above here, okay? So let's say so if R is positive, I already showed you when R is high, Y tends to be high. When R is low, R tends to be low, and that results in a positive R. Okay, well, let's see. What happens when X is high? When X is high, that means that this value will be higher than the mean, right? So that would give you a positive value. And then when X is high, this would be positive because standard deviation is always a positive. The covariance is part of calculating the slope. Yes. Yes, 1. Okay, so when X is high, that would make this high, and this would be positive, and this is already positive, so this is positive. Then Y is high because it's a positive relationship, so this would also be positive, so that gives you a positive. So it's a positive times a positive, so it's just an average of these multiples. That's what this R becomes. Looking at the relative relationship between what X is doing with Y and multiplying these standardized values, right? So we subtract the mean and standardize it, make it relative to the mean. I don't want to spend too much time on that, but you can go back and look at what you learned about R. So what about if it's below the mean? If it's below the mean, if X is below the mean, this will be a negative, right? Because this value will be below the mean. It's a smaller value than X bar, so this is a negative. And then Y would also be below the mean if it's a positive relationship. So this would also be negative. But a negative times a negative makes a positive. So you continue to add positives to positives, and that's what makes R positive. It's the opposite if R is negative. If R is negative, what happens? So if the relationship was a negative relationship, downward sloping, then we talked about how when X is above, Y is below. It behaves opposites. So what's going to happen when they're opposites? When X is above its mean, this one will be positive. But then Y is below its mean, this one will be negative, because this will be smaller than this to be below. And you'll be multiplying a positive and negative, and that will give you a negative. And that, if that happens also in the reverse, that will add to the negatives. Okay, so this is a way of illustrating the relationship. If you didn't follow that, please review the video. But basically, these are all the same formula, and they're used for different illustrative purposes. Now, finally, the slope. Now, the calculator gave you the slope. How did it find the slope? When you have two variables and you're calculating, you're converting the scatter plot into a line. Now, here it's perfect, but that's rarely the case, right? When you're converting the scatter plot into a prediction line, the slope is found using calculus, actually. What's done is the line is chosen so that it fits closest to all the points, so that the residual value, the distance between the line and all the points is minimized. So that makes more sense if I made a graph like, my line is here and my scatter is all around. This is XY. All right, so the idea would be to float a line so that it's closest to all the points. And what you do is you minimize the distance between the points and the line. And the best line will be the one that does that best. Okay, it's the best fit to minimize. And essentially what you're doing is you're lying it down so that the distance from the points to the line in the top and the points to the line in the bottom cancel each other out. That's actually what ends up happening. So you don't need to do calculus in this class. You just get to use the results of calculus. But in future classes, if you go on in finance, you'll learn all about that. This is a simple way of finding the slope that you may have learned in statistics, or you're going to learn in statistics. This is the formula for finding the slope, and it does depend on the correlation coefficient times SY over SX. This relationship here can be used alternately. You can use it to find the slope, or you can use the slope to find the correlation. I created this easy mnemonic device here to remember the order, but you get to see all the formulas, so you don't have to memorize anything. But in a situation where you would have to memorize, let's say you were taking the CFA exam, you would have to memorize this, so you need to remember that the slope is calculated by R SY over SX, which spells, for me, R, the Y is first, and then the X, Y on top, divided by X on the bottom. It spells risk, because B is a measure of risk in finance, okay? When you plot X as the market returns and Y as some other stock returns or individual stock returns, B, the slope of that line, of the best fit line, is a measure of risk. So if R is positive, the slope is positive. So there is a relationship between the signs. Note, when R is positive, but they're not necessarily the same number, that's the point I want to make. B is positive, but they are different values. They could end up being the same, but they are different values depending on the SY and the SX. These are positives, right? Standard deviation is the square root of the variance. These are always positive values. Questions? So when there's so slope is a different concept than R. Slope gives the direction, the slope of that relationship. R gives you the strength of that relationship. Of the line. And B, to the strength of fit and the direction of the line, but B just gives you the slope of the line. And we're just doing this for 2 variables at a time. So the covariance is used to calculate the correlation, and the correlation is used to calculate the slope. So they are, it's not really a prediction, they are the same thing. I mean, they're used to calculate each other. Okay, questions about ex ante data? I mean, ex post data, historical data. And just reiterating, I need you guys to know this. The strength means the fit to the line, how fit they are to the line. The closer to 1 or -1, the better the fit. No questions, my 19 watchers? Now we could do the same thing in a different way when we get ex ante data. Now remembering that the ex ante data represents the distribution for 3 states of the economy. We have taken together historical data, we've taken together predictions of market performance in the future. We've taken some information on fundamentals of this company's stock and future prospectus. We put it all together and created this distribution with 3 possible outcomes. If the economy experiences expansion or boom, these are the returns. If the economy is a normal state, these are the returns. And if we fall into recession, these are the returns for both the market and this particular company's stock. And these are the probability of things happening. This would be the normal state at 50% chance. Okay, so this is actually a discrete distribution, just to be clear. I think I mentioned it last class, discrete distribution, because there's only 3 possibilities. That avoids calculus that you would have to use if it was continuous distribution. So see, this is easy. This is easier than if I had to teach you calculus. So the formulas are slightly different, but they're more general. They're more generalizations of the ones above. We use the Greek letters. Oh, hold on, I gotta freeze everything here. Freeze everything together because I don't know what I'm doing. All right. We're using the Greek letters because this is a distribution. The mean the mean is the weighted average, and it's represented by mu. I put a little x on it, and this should have a little x on it too. I lost the x. This has a little x there too. This is the weighted standard deviation. This is the weighted covariance. This is the weighted correlation. So these symbols should be to simplify things, but you could always think in terms of the other formula if it makes it easier in your mind. But this is just for the case that you have a distribution or ex ante type data. Mean, standard deviation, covariance, correlation, which looks easy like this, but don't lose sight of what it is. It's the covariance standardized. These are just the other variations of the formula that you probably won't use, but I just don't want you to forget them. And that brings us to the slope. The slope is calculated by risk R, which is the correlation. That's the Greek letter for R, if you didn't know it. And it's pronounced rho. Greek letter for R. R for correlation. And this is the standard deviation of Y. This is the standard deviation of X, so it's still R SY over SX. And we call this the beta. So you should have seen this before. You should have seen this in 3106. Let me know if you never saw this before. I'd like to know. Now this one, you probably want to use your Excel. If you have an HP calculator, this is done in HP. I don't know about the TI-80, but the TI 10B2 Plus does not do this weighted calculation. It's not possible. So, how is that so far? So everyone's learned beta before? So I can just zoom through the next stuff. So what I have for you is handout 3.5. 3.5 has the solutions like all solved manually. You should know how to do that too. So you need to know how to compute it manually. You need to know how to use Excel or well, anyway, if you have the HP 10B2. But it's not going to be directly from the BA2 Plus like the other one above is. So that is that. Let's take a 10-minute break. Not 10 minutes, sorry, 5-minute break. I need to send you some things and we'll get on to the next bit. Let's take 5 minutes. Meet you back here. Please write your questions in the chat and I'll answer them when I get back. I'm back. Just sent you a bunch of documents. These are the documents for the next test. And there might be more, so you should work through them. Let's see if you have any questions. No questions. All right. So I'm going to just show you what I sent you and where we're going to start. So I sent you okay, 5.5 and 5.6 are just the solutions to the last document, and I've done the manual calculations. So this looks familiar. So we did this one together for 5.6. You can work on this on your own, and you will find, I have all the answers there, so you just make sure you can get them. Like I said, work with Excel if that's easier, just to check your answers, but you will find in the end that the correlation is 1 and the slope is still 2. Now you can't see it visually when you look at ex ante data, but you can calculate it. It turns out to be 2 as well. Same interpretation of sensitivity. So that's those two documents. So that's 5.5 and 5.6, and that brings us to a formula sheet that looks like the one we've already seen, but I've transformed the formulas to look like finance formulas rather than statistics formulas, and I've put R's in here for return. So you'll see these formulas, don't be intimidated by them. This is just for finance symbols, right? R, and then I use a hat rather than S, and that's how the notes are and how textbooks are often. So that's just supposed to help you. Don't have to memorize any of that. Just recognize that that's a mean, that's a standard deviation, that's a covariance, that kind of thing. This is correlation where you standardize covariance. This is your risk term for beta, and then we're going to talk about another form for beta in a bit. And that's it. This is for ex ante. Again, similar formulas, just there's R's all over the place. R for return, because we're going to work with financial data and returns to the market. That's the M here. And the returns to the stock, individual, I for individual stock. Or index really is what it is, but I'll call it individual. So these formulas are analogous to what you've seen before, just for financial data. Even your slope, right? R, SY over SX, it's just more specific that it's between the individual stock returns and the market, M for market. But that's just like X and Y, or sorry, Y and X.